To recap, a solid disk with mass m of 18 kilograms and radius of 1.3 meters spins around a vertical axis. Through the disk center, a device of negligible mass is mounted at the disk's edge for catching, holding, moving, and or releasing a ball. The ball has a mass of 1.4 kilograms and can be treated as a point mass. Right there. All right. So last time we went over the first two questions, 7 and 8. Now we're going to address 9 and 10. So 9, now the disk is initially spinning without the ball with the angular speed of 1.3 radians per second in the blank, probably some sort of picture, counterclockwise direction as seen from above. And a ball is thrown at velocity initial of 3 meters per second relative to the ground and is caught at the edge of the disk on the side that is moving exactly in the same direction as the ball shown in the figure. What is the final angular speed of the system? Okay, so we're going to draw a picture. Ooh, we already have one up here. We'll pretend that this is spinning this direction and this ball is thrown this way, so that it is caught at the edge right there. You can see that they're both moving in the same direction. So first thing we want to figure out is moving exactly the same direction as the ball. First thing you want to figure out is which one's going faster. Is the disk spinning faster? So does the ball push the disk, or does the disk catch the ball and spin the ball faster? So we're going to start by converting the speed of the ball to an angular speed. You might be like, wow, it's moving in a straight line. How's there an angular speed? Well, once it gets caught, it starts moving in a circle or angular rotational manner, and that circle then will have an angular speed. So there's a relationship between the two. And that relationship is, let's see, x equals r theta, v equals r omega, and acceleration equals r alpha. So this is the one we're going to go for, and therefore we're going to say omega equals v over r. Omega ball initial will be 3 over the radius, which I think is also 1.3. There seems to be a lot of 1.3s involved. Yep, 1.3 meters. So it's kind of the edge of the disk, which is 1.3 meters. So we have 3 over 1.3, which is like what, 2.3? On 3 divided by 2.3, we get, no, we'll do 1.3. 3 divided by 1.3, we get 2.3077. 2.3077. This will then be in radians per second. Okay. So 2.3 is greater than 1.3, therefore the ball will actually speed up the disk. So we can actually look at some of the potential answers right now. And we're like, all right, we know it speeds up the disk is moving at 1.3, so we're down to 2 answers. 50-50, it's a good start, Okay, so now we need to find out how much it speeds it up by. So this is a collision. You can think of it as a normal collision, where a linear collision. Two things hit each other, and then they stick together as one thing, because the ball collides with the disk, and then they move together as one functional unit. So you have two types of collision. You have elastic and inelastic. I remember that for elastic, it's the kinetic energy is conserved, and inelastic kinetic energy is not conserved. But for both of them, the momentum is conserved. So what we're going to do is we're going to say that initial momentum ball plus initial, this is the angular momentum. So of disk initial equals angular momentum final of the ball disk system. And we know that linear momentum is P equals mv. Angular momentum then will be I omega. And that's just m, basically the analogy for m in angular is the moment of inertia, and the equivalent for velocity in angular is omega, which is radians per second. So that's more mnemonic than derivation. Okay, so we then are going to use this equation right here that we wrote out, and we're going to, we're just going to start going for it. So this will be the moment of inertia for the ball, which is mr squared, because we can treat it as a point charge. So it'll be m ball r squared, and this will be the radius of where the ball is rotating, which is the edge of the disk, plus times the initial angular velocity of the disk, ball, sorry. So we're using this equation right here, and we're just writing it out for the ball, plus now the moment of inertia for the disk is 1/2 mr squared, so it'll be m disk times r squared, which will be the same r, times the angular speed of the disk. And this will equal, I'll do this, I ball disk times omega final, which is what we want right there. Okay, so we'll do some simplifying. So the mass of the ball, I think, is 1.4 kilograms. So we can factor out an r squared here. So we'll have r squared times 1.4 times 2.3, which is the angular speed of the ball, as we found earlier, plus 1/2 times the mass of the disk, which is 18, times the speed of the disk, which is 1.3. Says right up there, 1.3. I have 1.3s. I'm going to solve this. Radius is also 1.3. So calculating this using the calculator, we have 1.69, which is 1.3 squared, times quantity. This will be 1.4 times 2.3. Yep. Plus, this will be 9 times 1.3. Yes. Now we get 25.2148. 25.2148. And these velocities aren't squared. They are not squared because they are momentum, not speed, or not energy. Energy is 1/2 mv squared. Momentum is mass times velocity. And we're doing conservation of momentum. Okay, so now we want to find this. We know that this will equal the moment of inertia of the ball disk system times omega final, and they'll be moving at the same rotation. So for this, we're just going to add the two moments of inertia of each of them. So this will be, we'll start with the ball, which will be m ball r squared, plus, then this will be the disk, 1/2 m disk r squared, and then we times omega final. Factor out the r squared, mass ball plus 1/2 mass disk. R is 1.3, so this will be 1.69, 13 squared basically. And mass of the ball is 1.4, this is 18, so it'll be 9 plus 1.4, which will be 10.4 equals omega final. So we can do, times omega final. So we can figure this out. So we'll do 1.69 times 10.4. That gives us 17.57, 17.576 omega final. Dividing this side by that, we have omega final equals, So we do 25.2148 divided by 17. 17. I'll just do second answer. There we go. And then I probably have to delete a piece. There we go. Does that work? 1.435. 1.435 radians per second. And the answer is, I probably did a rounding error because I think it's going to be this one right here. Probably some sort of rounding error. It's close. Yeah, it was close. If I'd just been a little bit, close. If I rounded it twice, then it'd be exact. Okay, so, and then this one's just a little bit too small, I suspect. So what happens here is if you looked at it just in terms, the ball had a bigger effect on the overall momentum than the disc did, because the ball had all of its mass at the outside. So you have that's a terrible disc. It's about the same. And the ball here, because the moment of inertia of the ball is bigger because all of its mass is further out from the axis of rotation. And so you have to plays a bigger role than the disc does, as a bigger role than its mass would suggest. And I imagine if you, so here the moment of inertia is mr squared, and the moment of inertia of the disk is 1/2 mr squared. I imagine if you forgot to take into account that 1/2, then you'd probably get something like the 1.37 radians per second. But the ball played a bigger role with respect to its mass than the disk did. Okay, so that is how we solve that part right there. Just conservation of angular momentum. Think of it as a normal collision. Okay, so then we move on and we're like, all right, now we want to compare the total mechanical energy of the disk ball system before the ball is caught by the disk with the total mechanical energy. And we're talking about energy kinetic, rotational, linear, and then probably potential energy. But there's not really a potential energy gain because we're all assuming it's at the same height. Ball after the ball is caught by the disk. Okay. So this is a collision. So if we think of it just in terms of a normal collision, you're never going to gain kinetic energy from a collision. You have two things hit each other. At best, they'll be equal. So this is a potential answer. But more than likely, you're going to have before is going to have more energy than after. So more likely before you're going to lose energy in the collision. And since it seems to be an inelastic collision because they come together and they stick, you probably are going to have this one here. It's probably not going to be, this is an inelastic collision. This is an elastic collision. And this is just impossible. So we've already narrowed it down to two possible choices. Cross that one out. And since they didn't bounce off of each other, I'm guessing it's probably going to be this one, because if you had inelastic collision, the two would come together because they're coming at different speeds and then bink, and then go off on their own separate ways. But since they specifically stayed together, there's probably some energy lost there. And so that'd probably make it an elastic. Elastic, inelastic, totally backwards. So there was not conservation of energy. So not conservation of kinetic energy. So that is the reasoning for what the answer probably is. But if you have time, which you probably won't, you would want to actually calculate this out. So we have energy kinetic initial, energy kinetic final. And so energy kinetic initial would be energy kinetic initial from ball plus energy kinetic initial disk. And the energy kinetic equation is 1/2 mv squared, which has the analogous 1/2 I omega squared for rotational. So for the ball, we're just going to use the 1/2 mv squared because we know it's linear speed. 1/2 mv squared, and we can treat it as a point charge. This will be ball. And we'll do 1/2 for the disk. The moment of inertia disk, 1/2 mr squared times its rotational speed, which is 1.3 radians per second. And this will be squared. 0.3 squared. Nope, that's supposed to be squared. And we can calculate this out. I'll leave a little space Let's see, this is going to be 1.4. That I think was 18. So we take this on clear. Did I want to clear that? Maybe. 0.5 times 1.4, and then it was 3 meters per second. So we have 6.3. 6.3. And then this will be 0.25, which is 1/4, times 18 times 1.69, which is 1.3 squared. And then we'll have another 1.3 squared, which would be another 1.69. We get 12.85. Yeah, 12.85. Add those together, plus 6.3, and we get 19.15. 19.15. That will be joules. You can combine the linear kinetic energy and the rotational kinetic energy together because they're both measured in joules. Even though the equations feel different, these things can be combined. Okay, now I want to find the energy kinetic final. Energy kinetic final. This time we'll have to use the rotational one because, well, yeah, it's easier to use the rotational because they're rotating together. We could actually use the kinetic by converting the ball back to linear, but not worth it. Not worth it. So, well, the moment of inertia here is just going to be the sum of the two moments of inertia because they're moving at the same speed. And so that's going to be m ball r squared, because the mr squared is for a point charge, or point rotating. And then 1/2 m disk r squared for the disk, and then omega squared, which we know we can factor out in r squared, m ball, which is 1.4, plus 1/2 m disk omega squared. Putting some numbers here, we have 1.3 squared, and then this is 18. 18 divided by 2 is 9, plus 1.4 will be 10.4. And then we'll multiply that by the final speed, which we decided was 1.44. Or 12 squared. Not related, completely coincidental, not actually exactly 1.44. Okay. So we do 1.3 squared times 10.4 times 1.44, and we can't forget to square this. We square it. Ooh. That seems big. Interesting. Did I mess something up? That seems too big. Did I? This is what I did. So, right here, 1/2 mv squared, 1/2 I omega squared. So everything here has to be divided by 2. Bush League, amateur, that's the real crime here. Not being professional. 18.22. There we go. Bam. So, this is joules. So this is the final energy. This is the initial energy. The initial was bigger than the final. So energy, kinetic energy, was lost during the collision. And therefore, this one is wrong. But this answer, energy kinetic before, is greater than energy kinetic after, which is what we suspected, though we weren't entirely sure. So on this one, if you have time, prove it, kind of reassure your assumption. If you don't have time, but they didn't clink against each other and bounce off, therefore probably an elastic collision, therefore probably not conservation of energy. If the ball had been moving at exactly the same rotational speed as the disk when they came together, then it probably would have lost no energy. But since the ball was moving faster and it actually sped the disk up, that's probably where the energy loss came from. So this is a fairly challenging problem. I hope looking at this helped, and I will see you next time.